A big thank you to the Talk Python team who sponsor this episode of the podcast. If you want to get better at Python, now is an excellent time to take an online course. Whether you are just learning Python to delve into great topics like artificial intelligence, or you need to go deep into things like APIs and async, my friends at Talk Python Training have a top-notch course for you. Visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my Patreons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I am very honored to have Andrew Barto on my show. Andrew is a former computer scientist and professor emeritus and known for his research on learning in machines and animals. He worked on developing learning algorithms that are useful for engineering applications, but that also make contact with learning as studied by psychologists and neuroscientists. When it comes to reinforcement learning, short RL, it has been immensely gratifying for Andrew to participate in establishing new links between RL and methods from the theory of stochastical optimal control. Especially exciting are the connections between temporal difference, short TD algorithms, and the brain's dopamine system. Plenty of people know him as one of the authors of the great book Reinforcement Learning: An Introduction, which he wrote with his colleague Richard Sutton. And now, ladies and gentlemen, here's my podcast with the one and only Andrew Barto. Andy, it's an absolute pleasure and honor to have you on my podcast. Welcome first of all. And what we want to start with is, of course, your early days, how you started and got into RL. So you know yourself the best, so maybe...
Okay, well, it's a pleasure to be here, and thanks for inviting me. I can begin. My dad was a mechanical engineer. My mother was an artist, later became a nurse, and I've always been interested in engineering and artistic kinds of things. And I ended up going to the University of Michigan to study naval architecture, which I thought was a nice combination of engineering and architecture. I did that for a year and decided, well, it wasn't really what I wanted to do. And I dropped out. I went into mathematics and got an undergraduate degree in math. And at some point along the way, I don't remember when, I got interested in I think I read or heard about McCulloch and Pitt's idea of artificial neurons being related to logic circuits in computers. And so for graduate school, I applied to the University of Michigan again, where I lived, in computer science. And so I entered the graduate program and wound up studying, lots of things. It was a very interesting period. It was a kind of unique graduate program there. And I ended up in a lab called the Logic of Computers Group, which was directed by three professors, one of whom was John Holland, the originator of genetic algorithms. And another was Arthur Burks, who is an electrical engineer and a philosopher, very distinguished professor who actually completed von Neumann's book on self-reproducing automata. And Bernie Ziegler was studying modeling and simulation. And so the three of them had this NSF-funded group. I became a research assistant in it. And so the whole atmosphere was really focused on genetic algorithms on the one hand, and cellular automata, which is what von Neumann's self-reproducing system was formulated as a cellular automata, and then modeling and simulation. And I wound up doing my thesis were really working with Bernie Ziegler. We were modeling the modeling process in terms of systems theory. Mm-hmm. And so my thesis was playing out some of these ideas in the realm of cellular automata. So I was sort of in that mix of things. I wasn't a typical computer science student. I've only taken 2 courses in programming in my entire life. And although I taught Fortran for many years as a graduate student, I've never been a hacker. So I skipped that stage for some reason and was really interested in these biological connections, and the idea of cellular automata was very appealing because with very little specification, you can generate enormously complex behavior, and that kind of that sense of the discrepancy between what needs to be specified and what the consequences are was something that appealed to me. I was heavily influenced by John Holland and genetic algorithms, but I never really bought the algorithm in the sense of I felt that there were a lot of other stochastic algorithms, optimization algorithms that could compete with genetic algorithms. But I was influenced by the idea. And so combining that with an interest in neural networks led to some of our earliest reinforcement learning systems. Mm-hmm. Let me back up a little bit, because then I got my PhD and I took an assistant professorship at the State University of New York in Binghamton, which is now called Binghamton University. And it was a very interesting program focused on general systems theory. And I was there for just 2 years. I didn't really buy the general systems theory perspective that was prominent there. And I heard of a postdoc at the University of Massachusetts on a project studying adaptive neural networks. And this was 1976 or 1977. And so no one was really studying neural networks, but I was interested in that. And I drove up and talked to Bill Kilmer, I was hired as a postdoc. I took a leave from my assistant professorship and went to Amherst and worked on this interesting project. I eventually resigned my assistant professorship to continue the postdoc, which is something I don't recommend students doing these days. But it turned out to be a good move. I eventually became a faculty member at the University of Massachusetts in Amherst and stayed there until I retired just a few years ago. But reinforcement learning, I guess, when I went to Amherst, the project that I was a postdoc on was funded by the Air Force Office of Scientific Research. And it was a project that was instigated by Harry Clough, who was a physiologist who worked for the Air Force and had the idea that neurons worked to increase something and to decrease something else. He called it the theory of the hedonistic neuron. And the project, whose principal investigators were Bill Kilmer, Michael Arbib, and Nico Spinelli. They were professors at UMass and had gotten this Air Force contract to see if Clough's ideas made any sense, see if they were worth studying and pursuing. And I became a postdoc on that project. And not long after that, Rich Sutton, who was who had recently graduated from Stanford, joined the project as a research assistant. Mm-hmm. And so Rich and I really began working together, I guess 1977 is basically when this began. And our project was to see if Harry Clough's idea of the hedonistic neuron was something interesting and whether it was worth studying. So that's what we began doing. And the surprising thing to us was that the idea of learning by trial and error, which is what Clough said neurons might be doing, was not really well studied. It's not supervised learning. In fact, to this day, I think many people don't really understand the distinction between reinforcement learning and supervised learning. And most of the work that was being done, not everything, but most of the work was supervised. And reinforcement learning uses a less informative teaching signal, a reward or punishment signal, rather than a specification of a desired response, which is what supervised learning systems do. So we were surprised, and we had the leisure at that time. It was a 3-year grant or contract, and we were able to pursue a lot of ideas and to really study the history to see if these ideas had been worked out and were they worth anything, had they been shown to be useless, and so on. And so it was a very, it was a very interesting period. And we found that, some work had been done, but it hadn't really, we felt it hadn't really been appreciated. It was really, became what is now reinforcement learning. We were not the first. It goes way back to many earlier people, specifically in psychology. The idea of Thorndike's
the puzzle box, right? Thorndike's puzzle box.
The puzzle box, and the cat in the puzzle box is trying out things, and eventually stumbling on something that lets it escape from the box, and he put it back in the box, and it would get out in less time, and eventually it would immediately let itself out of the box, and he did this with fish, not the same box, of course, but he did it with other animals, and this became called trial and error learning, and it's different than supervised learning because no outside agency was telling the cat or the other animals what they should do. They had to discover it for themselves. And so this is what Clough postulated that neurons do as they're operating in a nervous system. So we concluded that it was an interesting idea, hadn't really been exploited. In fact, it had been rejected by AI researchers as being too weak. And in psychology, it was associated with behaviorism, which had been rejected to a large extent in favor of cognitive psychology. And we felt that, there were many valid criticisms of behaviorism, but in some sense, it was like throwing out a simple principle without really sort of throwing the baby out with the bathwater, so to speak. Mm-hmm. And so, this very simple principle, very, very well supported empirically, but had been relatively neglected certainly in AI. Although some early AI, particularly Marvin Minsky, worked with his thesis was a reinforcement learning thesis, or at least part of it. So those were exciting times, and I became a faculty member. Rich was my first student, and I have to say that the whole development of this owes a tremendous amount to students that I've had. I've had fantastic students. Rich was the first, but followed by many others who, just wonderful, creative creative people who've gone on, in most cases, to really do some great things. So, I really owe so much to my wonderful students. But and one of the first things we did in this project was build what we call an associative search network, which was really combining an associative memory idea, which was prominent in the literature at that time, correlation matrix memories and so on, but they were supervised. And we created one really by combining sort of Holland's ideas of search with the associative memory, and we came up with the associative search network, which stored memories, but no system told it what memories it should store. It had to discover them to see what produced the most reward. And so that was sort of an early few papers that we wrote, and then continued from there. But so that's probably well enough of my early. I sometimes think I should have been an architect rather than a computer scientist. I'm an atypical computer scientist because I'm really not interested in computers. I use them and have always relied on tech support. People ask me questions about computers, and I say, "Ask my son. I have no idea." I'm an atypical computer scientist.
Mm-hmm.
So RL.
Could you maybe define, Andy, maybe in simple terms, what is RL? How would you define it? You did it earlier on in a little bit in a crisper way, but maybe if you want, you can go longer.
Well, to me, the principle is at root, it's search. Just trial and error is search. But in addition to search, it's memory.
Mm-hmm.
So it's search plus memory. And so the results of search are stored so that the search can be eliminated, because the consequences of search are stored in memory so that you don't have to continue the search. And so it's not just finding a good solution, it's saving it. Mm-hmm. So I think those are the main principles. Now, I think a lot of people then associate reinforcement learning with temporal difference algorithms for doing prediction. So this was really Rich Sutton's thesis, adding a predictive element to this. And that greatly increases the power of these systems when there's a delay between an action and the consequences. But RL to me is more basic than that. It's a trial and error search plus memory. And prediction augments the power of that. So that's, I recently wrote a paper that appeared in AI magazine that talks about this idea of search and memory. It's actually memoized search, if the term memoization means something. Mm-hmm. And so instead of computing each time, you can store the result and avoid the more complex computation process if you have the same problem to address again. And so memoize, it's not memorized, it's memoized. It's a term created by Robin Popplestone, who I was fortunate enough to be a colleague with him at UMass for several years before he passed away. And he and Donald Mickey created the idea of memoization. And I think of RL at the base is memoized search. So I don't know. It's a pretty abstract definition,
But
but
it's very understandable, Andy.
okay, good.
Going back to languages, you mentioned early on that you taught people in Fortran.
Yes.
What language did you use to implement your first algorithms? Was it also Fortran or C?
Oh, gee, gosh, that was so long. No, C, I don't even think existed then. I'm not sure when C first appeared. Um,
A bit later than the 70s, I guess.
so we did some work using APL,
Okay.
which I don't know if anyone, it's an interpreted language with a strain, you need a different keyboard and so on, but it's very fast to implement things. But then I think, my students were using C eventually and Lisp in some
Yeah.
cases. Uh, but and I wrote programs in C when I was I haven't written a program in many years, however. So and now a lot of people are using Python, and yeah. So APL, very strange language. People prided themselves on writing the most unintelligible code possible in APL, and of course that's not the preferred approach these days.
Yeah. Would you say that there is, on one side, there's this extrinsic motivation, right, of in terms of reward, and there's also this intrinsic motivation where you are intrinsically motivated to do something. What would you say in RL in these typical algorithms that we use that you know about? Are they extrinsically motivated because there's this common thing called reward, or is there also a component for intrinsic motivation?
Oh, that's a very good question. Yeah, I've been very interested in intrinsic motivation, and I think, I mean, the way to think about it is an RL system has this reward signal, and in most cases, you think of it as coming from the external environment of the robot or whatever system is the learning system. But if you look at us, you look at animals, the reward signal in our brain comes from our brain. It's generated inside the organism. Um, it can be triggered and influenced by external inputs, but there's no sensation that we have for reward. It's something that parts of our brain that evolved over many long epochs. Our brain generates these reward signals, so all reward to me is generated internally to the robot or whatever machine you're inserting this reinforcement learning system in. And the difference between intrinsic and extrinsic reward then is not if it's generated inside or outside the organism, but whether it's targeted to a specific task, or whether it is a more general purpose reward that facilitates learning skills and knowledge that can be used for many different tasks. So I think a good analogy is the distinction between basic research and programmatic research. So the classic example is the work to develop the atomic bomb. That was programmatic. It was all directed to this very explicit goal. Whereas basic research is really developing knowledge that may or may not be useful, but often is useful. So I think AI systems need to have a basis for learning generally useful knowledge and skills. And I think intrinsic or mechanisms like what we call intrinsic reward and intrinsic motivation in humans, I think something analogous to that can be useful for AI systems to move away from being so specific, targeted to specific problems, but have more general, toward general AI rather than specific AI.
Mm-hmm.
And I think looking at my career, I've been largely intrinsically motivated. There are just certain things that interest me.
Mm-hmm.
And, I think even RL in the early days, it wasn't clear it was going to be useful, but it was interesting. And so, my work was motivated by this interest rather than to create a particular system to solve a particular problem. I think it's a shortcoming, and to some extent, of how my work has been, and many other people now have really taken it to actually do very interesting, surprising, like AlphaGo, the Go playing programs that DeepMind has produced. But I think my work is driven largely by being intrinsically interested in this confluence of ideas,
Mm-hmm.
search, memory, computation, so intrinsic motive. I think it's a misunderstood. It's a very popular idea now in among reinforcement learning people, and I think in many cases they really misunderstand it and use it as a general term for anything that is not the most simple kind of reward structure. And I've written papers that try to put it in context and relate it to psychology. Psychologists have studied this for quite some time, and I think a lot of people don't really get the distinction between extrinsic and intrinsic motivation. So anyway, it's a good question.
Thank you very much. What I also wanted to talk about is, how do you feel about this kind of resurgence, quote unquote, of reinforcement learning? How do you see that? You mentioned AlphaGo. Are you proud how far RL has come, or what do you think personally?
Well, yes, I'm astounded. Actually, there have been surprising things throughout. The first was Jerry Tesoro's backgammon program, TD Gammon.
Yeah.
And that was very surprising. And then the Go players from DeepMind, equally surprising. So it's been very gratifying to see that these ideas can be powerful in particular problems. I think there's certainly shortcomings of these systems that they're focused on problems, for example, where the reward signal is easily defined. In a game, it's a relatively transparent process to design a reward signal that leads to better play. In many other problems, it's not clear at all what the reward signal should be. But still, I've been, it really put RL on the map as being an important part of AI. And it actually, I think, helped sell a lot of our books. Rich and I wrote a book on RL, and the sales surged with the advent of the DeepMind results. So that's great. I can't complain about that. No, I think it's been very exciting. I'm concerned that there's hype about it. Not just RL, but deep neural networks. I mean, the idea of combining that with RL is a powerful thing, and it's been, I think, it's not all of AI. I mean, many people are right about it as being, but I think it's a component that will continue to be developed, but augmented by other kinds of algorithms. Yeah. So no, I'm very it was an exciting thing to see the performance of these systems.
I see.
And the Tesaro's backgammon, I forget the date of that, but that was surprising because RL has always had the reputation of being very slow, and it is slow. So that's a deserved reputation. But with a game like backgammon, the state space is so big that if you applied classical dynamic programming to it, it would take thousands of years, even on very fast computers. And so, Jerry Tesaro's system learned, I don't know how long, weeks of simulated play, which seems slow, but compared to what a classical dynamic programming method would take, it was very fast. And so that was a revelation that made it evident that RL could be a useful way of approximating optimal solutions to very complex stochastic optimization problems. So and then AlphaGo, so there's AlphaGo, and then there's AlphaGo 0, and then I think there's AlphaZero, and these systems take it further and have really demonstrated that combined with deep neural networks plus massive computational resources can do surprising things. So yeah, it's all very exciting. But I have to say, I retired some years ago, and I'm glad to be retired because it's impossible to keep up with everything. And,
that's
and
a
now
problem.
I really don't have to. My students are out there pushing it and keeping up with it and being key parts of the whole development. But I sort of, a lot of pressure was taken off of me when I retired because it's impossible, even for young people, it's impossible to keep up with the volume of literature that's being generated. Much of it very interesting and exciting.
Yeah, absolutely. I can speak for myself as a very, very beginner in RL. When you get started and then you see on Twitter, DeepMind published something new and you're like, okay, I just got started. It's a bit, can be a bit frustrating. You talked about pressure.
Yeah.
How was it in the old days when you released papers? You didn't have this kind of pressure what people have nowadays, right?
That's a very good point. We were funded by a 3-year grant or contract, and I was a postdoc. I wasn't teaching. Rich was a graduate student, and we were able to go pretty deeply into things and would publish. I think our first papers came out in 3 years. I think 81 were some of the first papers, and we started in 77. And we didn't feel compelled to produce a paper or a conference paper every year, like students and faculty today. In fact, there was not a venue for what we were doing anyway. So things like the big machine learning conferences really didn't exist. It was I think we'd worked for 3 years and published a bunch of papers after that, and then another 3 years, another bunch of papers. And today, people can't do that. And I think it's really unfortunate. There's a lot of pressure to publish 7 small conference proceeding papers, and often they're very good and influential, but there's a continuous pressure to generate a volume of these things, and I think that's really unfortunate that students are put in that position. I think in applying for jobs, they should request your top 3 papers or something like that, and not the number of them.
Yeah,
which is I think ought to be irrelevant. Should be the significance and the influence of the papers rather than the number. And in the old days, we were in an enviable situation to be able to work for relatively long periods without publishing stuff. So
the good old days, if someone would say.
The good old days.
You talked about Rich Sutton being your first student. What would you say your students back in the days when they said, "Hey Andy, I want to get started in RL or in neural networks in general"? Because there were these AI winters, right? There were 2, and one of them was from 74 to the 80s, beginning of the 80s. What would you tell them if they come to you and say, "Hey, I want to go into neural networks / RL"? Would you motivate them, or would you be like, "Okay, take it easy"?
Well, my students were always motivated. They were intrinsically motivated, and not all of them. I mean, there were a few that went on to do other things, but the ideas were, I think, just interesting ideas, and students who had those whose interests coincided with those things didn't need to be motivated. I would try to influence students so that they connected with the literature and that they knew how it fit into the historical context. And but my students, I was able to mostly allow them to work on their own ideas. And often, actually, the process that I ended up with, I thought of as being analogous to simulated annealing. So a new student would have kind of high temperature search among various ideas, and I'd say, write a paragraph about it. Don't worry about the English or language or punctuation or anything, just a quick, and then I'll give you some feedback, and we'll do this high temperature exploration, and then slowly we'll turn the temperature down as things head towards something that looks substantial enough to turn into a dissertation. And that it really means the students were working on their own ideas. I never had a project. Well, that's not quite true, but it was mostly working with ideas and encouraging students to generate ideas and to turn them into substantial scholarly pieces of work that could lead to a degree and publications. And so it was not as if I told students to write code for a specific component of a large system that we were building. They're really their own ideas. So I didn't have to motivate a large number of students.
That's fascinating.
I think the subject is just so interesting that
it is. Yeah.
That it didn't need. The challenge was to direct work toward things that I thought were not frivolous or lacking in rigorous support. And really succeeded in doing that for the most part.
And let me tell you that the book from you and Rich is really helpful. I would say thousands and thousands of people I have it myself, and it's such a big help actually if you delve into the field. So thank you very much for that.
Yeah. Oh, well, I thank you. I'm honored to hear that. I'm glad it has been helpful. Then there's a new edition now that's
we should say
much
that.
bigger.
Yeah.
And one of the things that I like about the new edition, there are many things, but there's a chapter on neuroscience and psychology that Rich and I intended for the first edition, but we never got to it. And so the second edition, which is much longer, unfortunately, but it has connections to neuroscience and to psychology, and I think those are very important. I like the fabric of these connections and how they relate to each other, rather than just specifying the current state of the art.
Yeah, I completely agree on that. That's also why the podcast is about engineering, neuroscience, and AI, because as you said, it's somehow interrelated.
Good.
Yeah. Before we wrap things up, Andy, was there a point back in the days where you didn't make any progress and you said at one point, okay, I want to give up, or did you always pursue your goal without thinking about?
There were times when I was unhappy because we hadn't made any progress for a while, or I felt that the ideas were justifiably criticized by AI researchers as being too weak, not able to, outdated ideas from behaviorist theories, too weak, not knowledge-based, and so on. And, those are reasonable criticisms, but, we made enough progress that I thought we were contributing. And then we would come up with something very interesting and continue. So, but there were periods when I, was quite depressed about what I was doing.
Mm-hmm.
But usually didn't last too long, especially with students who are so good, coming up with great things. It was a pleasure to work with them.
Mm-hmm. So to wrap things up, Andy, is there anything you want to say to the audience, maybe in terms of RL, AI, any motivating words from you?
Oh, yes. Well, as I said, I think it's important to relate what you're doing to previous work. And so I have strived to make connections rather than claiming that something we were doing was completely new. And I actually, at the first RL conference that was held at Princeton some years ago, I did a 10-minute introductory talk. And I said, don't be afraid of rediscovering the wheel.
Mm-hmm.
But if you do, call it a wheel
rather
than something else, or at least a new and improved wheel, rather than create a new name disconnected from the history. And but that's my perspective. Not everyone feels that these connections are important. Rich Sutton, for example, does not. He likes to disconnect from the past, and I'm the opposite. So I think we worked well together because of that, those differences. But I think that's how I think by connecting things to historical context, you actually build a field that has some not only computational power, but historically lasting influence on future work. So I think I encourage students to read even old papers. So I've been criticized for citing papers that were more than 10 years old, and I think that's a ridiculous criticism. But some of those old papers are extremely important, I think. So, and in our book, we tried to talk about the history, to talk about the influences and some of these earlier papers that we think were so important, like Arthur Samuel's checkers player, for example, which is still a very worthwhile thing to read about, I think. So,
awesome.
Yeah, I thank you for this opportunity. I don't know if what I've said made sense.
It made absolute sense.
And I'm delighted to see so many people interested in RL. You know, one concern I have is you have to be careful in, you know, putting RL systems out in the real world, because often you don't know what they're going to do. And so there's a lot of thinking needed to ensure safety of these systems. So that's important. I guess it's one of the reasons I got interested in RL, because the systems will come up with things that you never thought about. They're really creative in a sense. And that was appealing. But on the other hand, that can be a problem, because they may come up with something that, I mean, this is the basis of a lot of concern over AI that has been written about lately, in terms of, you know, the danger of AI. And I think that's an important issue, but it's also interesting that these systems are creative. So, yeah. Anyway, I enjoyed talking with you.
Absolutely.
And
what I wanted to say is, first of all, I want to thank you very much for taking the time, first of all, to be on this show. And I think I speak for a lot of people if I say thank you so much, Andy, for writing the book, for contributing to the field, because it's such an interesting field, and I'm just getting started. But if people want to jump into it, the book is very good, and I think it's excellent, to be honest.
Thank you.
And it was a pleasure sharing your ideas, hearing from your ideas on this podcast, and what your vision on AI is, RL, and so on. I'm really happy to have you on the show, to be honest. And
well, thank you again for inviting me. I'm glad to be able to do it. And yeah, so thank you.
Thank you so much. If people want to reach out to you, how can they do that? My
email address is, I mean, if you Google me, I think it comes up with my homepage, which lists publications and has links to the book.
Yeah.
Also. And so that would be the way. My email is on there. So, and I try to answer email in reasonably short periods of time. So, yeah.
I noticed that. Thank you so much, Andy. Take care.
Okay. My pleasure.
Bye-bye.
Bye-bye.